All right, really quickly, it is raining. I apologize if you can hear the rain, because I can hear it. So maybe you can hear it. Okay, but let's talk about static forces. And there's three examples. Let's see how fast I can get them done. Okay, I'm probably gonna take this is probably gonna be like a 30-minute video. We have a hanging traffic light example. When we call it the hanging traffic light example because this is kind of like a traffic light hanging from two ropes, right? Maybe it's got like one rope here that connects to like some sort of point where the two other tensions intersect. Okay, but you have two tensions that are both directed at the same angle from each other. Okay, and to solve our force problems, okay, we're going to start with step one by drawing the forces, draw forces acting, okay? And we're going to make, okay, the components, okay, using diagonal tensions, okay? Okay. So then our second step is to write an equation, write equations relating forces. Okay? So what I mean by writing equations that relate forces, right, means that I'm going to have a set of x direction equations and I'm going to have a set of y direction equations. Okay? Okay. So what I'm saying, right, is I need to have a set of x direction equations and a set of y direction equations. So what I would do to get the x direction, right? Okay. So I'm basically taking this in consideration. I'm basically calculating the forces with respect to that point where the chords meet. Okay. I mean, on the box, on the box, right? It's only really this tension, but we're talking about this one right here, right? Well, I've got T1, T2. Let's call these T1, T2, and then we've got mg of the box going down, right? Okay. And you should notice that T1 has a vertical component and a horizontal component. You should notice that T2 has a vertical component and a horizontal component. And those components are going to be equivalent to each other, right? Well, think about it. In the x direction, the sign isn't moving anywhere, right? The hanging traffic light isn't moving anywhere. So, really, what we should be saying, right, is that if this is ft1x, okay, and this is ft2y, or sorry, ft2x, okay, and then this right here is ft1x, ft1 or 2y. Gosh, I am really messing up on these symbols right now. Okay, then we should be able to say, okay, well, the x components should cancel each other out because there shouldn't be any. The net force on the whole thing should be zero because it's not accelerating anywhere, right? So in the x direction, we should say that the x component of the tension 1, okay, should be equal to the x component of the tension on 2. Okay? So that by that logic, we should see that ft sine theta equals, guess what? ft sine theta. Wow, who would have thunk, right? Okay. In the y direction, we should see that instead of the two may be equal to each other, okay? But ultimately, the y components of that are going up need to balance out the down forces. The up forces balance out the down forces. So what's going up? We've got ft1, fty1 plus fty2, and we can set that whole thing equal to mg, okay? And this is saying, well, the y component is ft cosine theta. The y component for the other one is also ft cosine theta, so we can set those equal to mg. And you can see that this becomes a simpler equation, 2ft cosine theta equals mg. Okay? And you get a really, and then if you wanted to get f sub t by itself, right, you would just divide by 2 and cosine theta on both sides, and you would end up getting that the ft, okay, ft is simply equal to mg over 2 cosine theta, okay? In this case, right, you would see that the tensions are equal to each other. They should be equal to each other. So the tension in one string is the same as both. If they're both at the same angle, right, and there's no other forces, right, then they should be the same. Okay? Okay, so there's that, right? You can see that we don't really get anything from the x direction. The x direction doesn't really tell us anything. It just says that they need to be equal to each other. Okay? That helps us prove that they're the same tension. Okay, hanging from ropes at two different angles. So if you have one rope that's at some angle theta 2, okay, and then another one that's at theta 1, so these are the angles that we're looking at, okay. Those are the angles that we're looking at, okay. You notice that theta 2 looks like to be a larger angle, right? Let me draw my forces acting on the mass real quick. We've got ft1 going up this way, ft2 going up this way. We've got mg going down, right? And what we should notice is that ft, the tensions, right? There's a vertical component up in the middle, and then it goes over and over, okay? Actually do it in the proper color here, okay? Okay, so right, you have the y component ft1, x component ft1, the y component ft2, x component of ft2, okay? So first and foremost, we need to look at our horizontal or x direction, right? We should see that the left forces, okay, must equal the right forces, okay? That makes sense because if the object's at equilibrium, so therefore, the only left forces that are there is the x components of the tensions. So ft1, so ft1 cosine theta 1 needs to be equal to ft2 cosine theta 2. Okay? So we should see that relationship there. And what you want to do now is you want to get one of these tensions by itself. Doesn't matter which one you do. Doesn't matter which one you do, as long as you get one of those tensions by itself. I'm going to get ft2 by itself. And so all I got to do is divide cosine theta 2 on both sides. And you end up getting an expression that's ft2 equals ft1 cosine theta 1 over cosine theta 2, okay? And that's, whatever, right? Well, we can't really do anything more with that. Let's just leave it there, okay? But let's move on to the other part, which is the up forces, okay? Up forces need to balance out the down forces, okay? How do we get that to happen? Let's see. So what forces are pulling up? We've got the y components of both the tensions pulling up, and then we've got mg pulling down. So what I'm going to do, right, is it should be ft1 sine theta 1, okay, plus ft2 sine theta 2, set that equal to mg, okay? Now, here's where things get fun, okay? Watch this. You see we got ft2 right here? Guess what? I'm going to substitute that whole thing in there. It's going to be a mess. It's going to be a huge mess. But you know what? I don't care. You got to make a mess to do physics, right? Okay, so you get ft1 sine theta 1 plus, and then you got now ft1 cosine theta 1 times sine theta 2 over cosine theta 2. Wow, what a mess this is, right? We're making a huge mess, okay? But you can actually make it a little bit easier for yourself, okay? Because if you look closely on that second term right here, you should see, oh, we got sine theta 2 over cosine theta 2. Hey, wait, sine over cosine is tangent, right? So we can actually make this a little bit easier for ourselves by writing this as ft1 sine theta 1 plus ft1 cosine theta 1 tangent theta 2 equals mg. Oh my gosh, and it's still a nightmare. It's still terrible to deal with. I still don't like it at all. Okay. But what you can do here now is you can actually factor out ft1, and that actually makes it to where you can get ft1 by itself in like a proper equation. Okay, so we get ft1. When we factor that out, we get sine theta 1 plus cosine theta 1 tangent theta 2 equals mg. Okay? And sorry, you can't see the mg because my window's blocking it, right? There you go, okay? And then when you isolate, when you get ft1 by itself, all you got to do is divide by this whole mess right here. And so you should end up getting that, and I'll write it off to the side here, okay? What you should end up getting is that ft1 is equal to mg over sine theta 1 plus cosine theta 1 times tangent theta 2. Oh my gosh, Mr. Mitchell, that's a nightmare and a half. Yeah, I know it is. It's terrible. Okay. Now, what you would do then, and I'm not going to do the whole step because it's just a waste of time. Okay. What you would do then, what you could do then, is you now have what ft1 is. If you take that expression and you plug it in for ft1 in there, you will get a new expression for ft2, a proper expression that is actually meets the requirements. Okay, and if you do that, you will have to do a lot of canceling out, a lot of rearranging, but you'll end up getting, and I'll just tell you what it is. You'll end up getting mg over sine theta 2 plus cosine theta 1, or sorry, theta 2, tangent theta 1. So did you notice, right? The only thing that changed here was that we swapped the angles, right? Instead of it being theta 1, instead of it being theta 1, now it pertains to theta 2. Okay. So there you go, right? That's that one. Okay. What a mess, right? That's a huge mess of an equation. It's terrible. Okay. Well, thankfully the next one's not that bad. Okay. The next one's not that bad because it's just going to be this hanging in the corner of a wall example. So it's important to note that for hanging in the corner of the wall, all that's happening is that your mass is being supported by two strings, and one of them is horizontal. One of them is horizontal, the other one's angled. Okay. The main thing to understand here, right, is that if everything balances out here, okay, if everything balances, okay, we can kind of set up a ratio. Okay. Since the ft1, okay, must cancel the horizontal forces, or sorry, since ft2 must cancel both other forces. Okay, so we know that ft2, right? This is the only one that's going to have a vertical component and a horizontal component. Okay. It's the only one that's going to have a vertical and horizontal component. ft1 is all horizontal, and then gravity acting on him is all vertical as well, right? So what's going to happen is I can set up this ratio that says, okay, ft2, the y component of that over ft2, the x component, okay, needs to be equal to the vertical forces over the horizontal forces. Okay? And so when I set this up, I'm going to put the y component of ft2, which, by the way, if I'm given this angle right here, the y component is opposite, so that's going to be ft2 sine theta over ft2 cosine theta. Now, what you can do here, if you wanted to, is, no, you don't want to do that. But I was going to say you could turn this into tangent, but no, there's no point in doing that, okay? And we can set that equal to the vertical forces, which is mg, over the horizontal forces, which is ft1, okay? So right off the bat, we should recognize that if these two have to be equal to each other, then we can get an expression for ft2, which is just, if we set ft2 sine theta equals mg, get ft2 by itself, it's just mg over sine theta. Okay? That's it. That's all you gotta do for that. Now, when I do that, okay, I've now got an expression for ft2, okay, and what you can do now, what you should be able to do now, is that you can take this expression, plug it in for ft2 cosine theta, okay, and that's what I'm going to do right here, is I'm going to take this part on the bottom, and I'm going to do ft2 cosine theta equals ft1, okay. I'm going to plug this in, mg sine theta, right? I'm plugging this in for ft2. Okay, mg sine theta times cosine theta equals ft1. And then you should recognize that, okay, well, sine over cosine is tangent, but if you flip it, you inverse it, then it's going to be cosine over sine. So this is actually 1 over tangent right here. So it's actually going to show us that ft1 is equal to mg over tangent theta. Okay? Just some shortcuts for you to know to get some tension stuff done. Okay, all right. Good on that one? All right, I'll be back for the next video, which is probably going to be the shortest video ever. So peace out, Girl Scout.